Hey, so today I'll try to do justice to air conditioners and move on at least to the beginnings of automobiles. They're both about moving heat and dealing with work associated with the moving of heat. The story so far with air conditioners, or I try to present to you, is that it actually is possible to move heat the wrong way from a cold object to a hot object that is against its natural flow, seemingly violating the statistics that drive heat from hot to cold. There's a cost to doing this because the law of entropy says that by itself you can't do that. That action on its own will lower the entropy of the universe, and that's forbidden. Only the law of entropy says that any thermally isolated system can never have its entropy go down. So complicated stuff has to happen if you're going to move heat the wrong way. And so my job today is to sort of give you an idea of how that works. And the way I want to go into that is first to make an observation, and then to play with these little boxes up here to sort of illustrate the movement of heat, both the right way and the wrong way, or that is, well, the way that goes naturally and the way that doesn't go naturally. So the thing to tell you is entropy, that is the measure of disorder in an object or a system. First, it measures every sort of disorder, so damage, crushing stuff, that's present as disorder, and then thermal energy is intrinsically disorder. And a question came in last time about whether that's a matter of a subjective issue, like what you personally consider to be an orderly room might be what another person considers disorderly and stuff. We're not talking about the sort of subjective issues of what's disorder. It's really an objective measure, and the order in entropy is an objective measure, the disorder of it, and ultimately it has to do with information. So there's a modern field of information theory that must have an awful lot in common with the world of statistical mechanics that is part of the world of thermodynamics. So one way of looking at disorder is how much information do you need to describe the system or the object at present. The more information you need to describe it and completely pin down all its details, the more entropy it has, because really the harder it is to, well, the more information. That's good. If the system has very little disorder, it is consequently easy to describe with few words. All right, so beyond that, the details of entropy, how you measure it and stuff, not so important. But one crucial observation, that is, thermal energy is part of the disorder. And thermal energy can be measured in the usual units of energy, like 1 joule. You can have 1 joule of thermal energy. Well, 1 joule of thermal energy added to a cold system, a cold object, so an object that has relatively little disorder already and therefore has low entropy. If you add 1 joule of thermal energy to that is very disordering to it. The first bits of craziness that you add to something that's otherwise completely sedate really messes it up a lot. So cold systems are especially sensitive to the addition or subtraction of thermal energy. You add thermal energy to it, its disorder goes up a lot. Big rise in entropy. You take out a joule of thermal energy, its order increases a lot, so its entropy plummets. Okay? So it is that way, and it's not so surprising. On the other hand, a system that's already hot and therefore has a lot of thermal energy in it already, and therefore a lot of disorder in it already, is not so sensitive to the addition or subtraction of thermal energy. You add a little thermal energy, who knows? Barely notice. Entropy goes up a smidge. Take out some thermal energy, again, barely noticeable. Entropy goes down only a tiny bit. So that observation then underlies the story I'll tell you, and what I'm going to put up there, if I can get this to work. I know I can, I just have to flip it backwards. Too many buttons. Okay. Hopefully you can see this. I hate to turn down the lights. The point of this is that I'm going to look at these boxes and I'm going to put thermal energy in and take it out and move it around. And this table tells me the relationship between the thermal energy in one of the boxes and the entropy in the box. So here's the story. These two boxes, I'm going to start them, supposedly they're representing two objects. What those objects are doesn't matter. Just pull them here. They presently have no thermal energy in them. So it's a sort of a hypothetical situation. They have no thermal energy in either one, and therefore these dials that I have here are both pointing at 0. Because they have no thermal energy and they have no other structure at all, they're just hypothetical objects. I'm just going to empty these guys out so I don't confuse myself. They have 0 entropy. So they have 0 temperature, 0 entropy. Nothing actually gets to this stage, but who cares? So what I'm going to do now is I've got two of these objects. I'm going to add thermal energy to the left object. So here I've got some thermal energy. I can easily add it in. All I have to do is bring something hot up to it and touch it. And when I do, 1 unit of thermal energy goes in. Thermal energy, plop, in it goes. And as it goes, according to this relationship between thermal energy and entropy, we go from when there's 0 thermal energy, there's no entropy. But if I put in that first dose of thermal energy, because this object was very cold, having no thermal energy in it initially, that 1 dose of thermal energy is really disordering to it. Its entropy skyrockets to 4. Poof! Okay? I'm going to put a second dose of thermal energy in. In it goes. And because this object already had some thermal energy and was therefore already warmer than absolute 0, that thermal energy didn't cause as much disorder. Remember, the colder something is, the more sensitive it is to thermal energy, and vice versa. So instead of going up by the entropy will still leap upward with that addition, but only by 3 more units, 2, 7. So I'm following my table. And my table is just, don't take the numbers too seriously. I picked them for convenience. They reflect the basic concept accurately, but they're not quantitatively meaningful. 1 more unit of thermal energy, and it goes, poof. And now we're at 3 here. And again, the entropy surges upwards with that addition of thermal energy, but by yet a smaller increment, by 2 units this time. Poof, to 9. And the 4th unit goes in, and we go up to 4 units of thermal energy, and that causes a small increase in entropy because we're already pretty hot, not very sensitive to thermal energy. It goes up to 10. Okay? So my addition of thermal energy to these objects, the pair of them actually, has caused a relentless increase in entropy. That's all good. The second law. The law of entropy is happy. This is all quite possible to have happen. The law of entropy says, fine, you can do that. Entropy's going up, we're good. Now, I'm going to touch the two objects together. Touch. And when I do that, thermal energy can move. I'm going to put away my package of thermal energy, and we'll say, what if one of the thermal energies comes out of the left box and moves to the right box? Well, before I do that, we'll remember we've got 10 units of entropy grand total in our system now. This is now a system, and I'm going to isolate it from the rest of the world, so no more thermal energy is going to go in or out, just between. So I'm going to take 1 unit of thermal energy out of this, and that by itself reduces the thermal energy on the left side by 1 unit and reduces the entropy from 10 to 9. So this by itself wouldn't, well, it doesn't even make sense because the thermal energy can't just live out here all up by itself. It's going to go over and drop into the other box. And when it does that, the other box gets 1 unit of thermal energy. The right box is bitter cold, absolute 0. It gets a tremendous increase in entropy as a result. 1 unit of thermal energy, the entropy leaps up to 4. Again, I'm following my little table. Okay? So 1 unit of thermal energy moving from the hot box on the left to the cold box on the right caused the total entropy of the pair to go up. We now have 9 units plus 4 units. That's 13 units, a huge jump in entropy. We started with 10 in my story. Does more thermal energy always mean more entropy? In a single object, if you do nothing else, you just simply add thermal energy to it, yes, the entropy will definitely go up. If you're allowed to do other things like reassemble a broken vase, now we can't be so sure. But adding thermal energy by itself is always disordering to any object, even the hottest object. It's just not very much for a very hot object. Can I incorporate liquid nitrogen into the lecture somewhere? Probably. We'll see. That means sudden escape. Okay, so 1 unit of thermal energy made the move, and the entropy went up. So the law of entropy is going, yes, I love this, do more. Okay, so we'll do more. Thermal energy, take another unit of thermal energy, and we'll move it across. When I did that, the thermal energy on the left goes from 3 to 2, and with it the entropy goes down by now a bigger jump because it's getting colder and it's more sensitive to the addition or subtraction of thermal energy. So that's what happened to the left side. The right side was cool, it wasn't ice cold anymore, or absolute zero really. So it goes up to 2 units of thermal energy, and that causes a rise, still a pretty big rise in entropy, from 4 to 7. So before that second unit of thermal energy moved, remember that we had 13 units of entropy in the total system. Now we've got 14, 7 plus 7. And I will claim now that's the most we can get, short of putting more thermal energy into our system, which would, yes, increase the total entropy, no matter where I put it. If we keep moving thermal energy, watch what happens. Now we're up to 14. Let's suppose another unit of thermal energy just by random chance tries to wander across from the left side to the right side. The left box goes down to 2 units of thermal energy, and because it's getting pretty cold, this is having a bigger influence on it. It goes from 7 units of entropy down to 4. It's getting more and more orderly. And the right side goes from 2 units of thermal energy to 3, and because it's getting hot, this causes a modest rise in entropy for the right box. So now we have 4 plus 9, 13 units of overall entropy. Uh-oh, entropy went down. So we moved thermal energy from left to right. That caused a drop in the entropy. The law of entropy forbids this sort of thing to happen. My claim that let me move it back. It wants to move back, right? It'll go back to this and this and this. This really is the maximum of entropy. This is the point, actually, given that the boxes are identical objects, they're at the same temperature. They've reached thermal equilibrium here. I started with, if you remember, I started with the left one hot, 4 units of thermal energy in it, and the right one bitter cold, no units of thermal energy. Thermal energy moved from the hot one to the cold one, causing the entropy to go up, the entropy of the pair to go up. One had entropy go down, the other one had entropy go up, but overall the entropy went up. And we've now reached the maximum of entropy, and the maximum entropy occurs when the 2 objects are in thermal equilibrium. And this is just generally true, that when you touch 2 objects together, one hot, one cold, heat's going to flow from the hot one to the cold one, and as it does, the entropy of the pair is going to go up. One will have the entropy go down, the other one will have the entropy go up, but the total will have entropy go up. And it will keep going up until they hit thermal equilibrium. And at thermal equilibrium, you have run out of, there's no more order to destroy. It's as disordered as it can get, actually. It's got the most entropy it can possibly have as a pair, and no further heat will flow. Any further flow of heat will actually cause entropy to go down, and therefore doesn't happen. So it all works out. Please log in again, really. Will heat stop flowing in the system when the entropy is highest? Yes. That is when heat flows down. Entropy tries to go to the maximum, as disorderly as possible. And the most disorderly possible arrangement of thermal energy in these two boxes is when it's distributed evenly, because they're identical objects, and their temperatures are the same. So that thermal equilibrium is the state of maximum entropy, maximum disorder, and is the natural thing that happens. It happens not only with temperature, but with any sort of disorder. If you take your sock drawer with the neatly arranged piles of colored socks, and you start shaking it around, it'll keep mixing and stirring. The entropy will keep going up, and it will keep going up until it's uniform. Everything's just as random as possible. And that's the point at which maximum entropy, that's where stuff stops changing. Okay? So, that said, in order to make heat move from between these two boxes, we got to do something deliberately. And the deliberate thing we can do is we can come into this system with additional disordered energy, or ordered energy. So it's a thermally isolated system, so I'm not allowed to bring in any extra thermal energy. If I did that, of course, I add disorder. If I reach in the box and pull out thermal energy, of course, I decrease the overall disorder. That's cheating. So at this point, I've drawn a box around a wall around the boxes through which no disorder is allowed to move. I'm allowed to move orderly stuff through it, which doesn't bring entropy with it. If I bring in ordered energy, like a charged battery, I bring the charged battery in, forget it that it carries any thermal energy. I can do that without violating the restrictions of the law of entropy. So I'll bring ordered energy into the system, and my goal is to make this box colder, and this box ultimately will become hotter. I want to chill this box down. This is this is your room, okay? So I'm going to bring in some ordered energy. I'm not going to drop it in this box. What I'm going to do is I'm going to turn it into disordered energy via some mechanism. So it's going to become disordered energy once it arrives. That is possible to do. It came in as ordered energy, but I'm going to grind it up into thermal energy, and I'm going to have it carry. The act of converting it is going to carry one of the units of thermal energy across. I think, will this work out? If this doesn't work out, I'll bring in two units of ordered energy. Let me just to be safe, I'm going to bring in a second unit of ordered energy. I'm going to turn it into thermal energy in the process. So now I've got 3 of these guys. So 2 of them came in as ordered energy. The third I plucked out of the left box. And I'm going to drop all 3 of them into the right box. Is it okay? So the left box went down by 1 unit of thermal energy, and that by itself drops the entropy of the left box by 3 units according to the table. But I dropped off. Is this going to work? Actually, I can do this without that extra dose of energy. So let me say I brought in 1 unit of ordered energy. Use that ordered energy to pick up a dose of thermal energy, and the 2 arrived over on the right side as 2 doses of thermal energy. You okay with me? Think before I do it. I made it unnecessarily complicated, and I'm undoing that. So on the right side, the left side, I've adjusted the dials. The right side, I have it. I dropped off 2 units of thermal energy. That increases the entropy from 7 to 9 for the first unit of it, and 10 for the second unit. All right? I'm at 14 units. So this is the math I was doing in my head, realizing that I can get away with this. I did not increase the entropy of the system. It stayed constant. I started with 14, back when I had 2 units of thermal energy here, 2 units of thermal energy there. I had 14 units of entropy in the overall system. By bringing in that extra unit of ordered energy, using it to pick up the thermal energy from the left side and drop both them off as thermal energy in the right side, I managed to lower the energy, the thermal energy and the entropy of the left side while increasing the thermal energy and entropy of the right side enough that overall the entropy stayed unchanged. And the law of entropy allows that. That's okay. Barely. It's right there at the entropy of this thermoelectric system cannot decrease. It did not decrease, it stayed unchanged, which is in itself, that's really, you got to get lucky to get that one to work. But I did. So the system now has 5 units of thermal energy in it. We started with only 4. So I managed to cool the left side. I should point out, the left side now has 1 unit of thermal energy. It is now colder than it was before that last transfer. So the last transfer chilled your room. The consequence is it heated the great outdoors by more than you cooled the room. The room lost 1 unit of thermal energy. The outdoors gained 2 units of thermal energy. It had to in order to satisfy the law of entropy. But it's okay, it worked. The law of entropy allows this. It can happen. This is how an air conditioner works. Only in concept, of course. Nobody, air conditioners do not operate on little paper discs with dials. But the idea is the important one, is that it is possible to move heat the wrong way from a cold object to a hot object. But you have to do it, you have to consume ordered energy in the process, and that ordered energy becomes thermal energy. More generally, you consume order in the process. Its association with energy is less important. It's the fact that by moving heat from a cold object to a hot object, as an air conditioner does, that by itself generates order that you don't deserve. So some other order somewhere else is going to get chewed up. And there are other forms of order than just ordered energy. Electric energy is a lovely source of ordered stuff, in fact, of order that comes roaring in through wires to your house. But other sources of order are ordered chemicals. You could buy natural gas will do this, because there's order in the natural gas and the oxygen in the air, and the fact that they're separated. You can burn one and the other. There's order in that, and so on. But the main thing is that you chew up order in order to move heat the wrong way. Any questions about that idea? The rest is all details. This incidentally is known as a heat pump. We have moved heat the wrong way. I think I've said this before in class, but I certainly said it in some of these videos. I now have filmed the automobile video too. A heat pump is one that deliberately moves heat from cold to hot. And it does that at the expense of order elsewhere. So it consumes order. Typically, the order comes in the form of work or something equivalent to work, which is electricity is equivalent to work. Electric power, electric energy is equivalent to work. Okay, the details now are in how you actually pull this off. And I told you that I gave you the simplest version of that last time. And that is, I was playing with a squeeze bottle. This is equivalent. It's just a syringe and plunger. So this is the syringe for your next flu shot. I should have a giant needle. Are you ready? Yes. Okay. I've plugged the end of the syringe. So just stuck a rubber stopper in there. So this is a screwed up syringe where I've got trapped air in there right now, and I can squeeze it to high pressure density and temperature, and I can unsqueeze it to low pressure density and temperature. And I showed you last time that if you compress gas and therefore do work on it, its temperature goes up. You uncompress it and have it do work on you, its temperature goes down. So that's okay with everybody? So the simplest of air conditioners would be, and we want to air condition this room, I go outside, I squeeze the air to high pressure and density and temperature. I let heat flow out through the walls of the syringe, which, yes, they're plastic, so they're not a good conductor. We could do better. I'd use a metal syringe, but okay, out goes the heat. It's kind of like wringing a sponge out, although the physics is somewhat different. Okay, you come in, And now let it expand. And it cools down, it becomes the coldest thing around, heat flows into it. And then we go out, and then we come in. And if you look at the process, I'm certainly moving heat from here to there, but I'm also doing work and having, or negative work on stuff. And if you add up the work I do squeezing and the work it does on me unsqueezing, I'm losing work. If you follow it carefully and you have to sort of sit there with do the numbers, I'm a net loser of work. I'm using up my breakfast cereal, in effect, to ultimately to do net amount of work on the gas. So I'm getting tired, okay? Where is the work ending up? It's ending up as thermal energy outside. So I'm taking in, say, 100 joules of heat from inside, and I'm dropping off 120 joules of heat outside. That extra 20 came from me, but they were invested as work. That was necessary to run the flow of heat the wrong way. All right? So what a heat pump does in general is it moves heat from cold to hot, and the amount of heat it delivers to the hot side is more than the heat that it removed from the cold side. And where did the extra come from? It came from the work required to power the system, to operate the system. All right? In a real air conditioner, this little trick with compressing the air back and forth isn't enough. They can do better. I mean, in principle, it works perfectly. In practice, it's not a very powerful system. It doesn't move enough heat fast enough. They can do better given the size of the machine. How do you do better? Don't use air as the material, the substance you squeeze and unsqueeze. Use more generally what's known as a working fluid. And the word fluid is the key here. Remember, fluids include both liquids and gases, and you make use of that. So the working fluids that are used in all the refrigerators you've encountered are chemicals that can be both liquid and gas at the temperatures involved in the heat pumping process. And an example of such a material is the stuff in one of these so-called air blasters. I mean, that's not got air inside. If it had air inside, it would be a gas at room temperature no matter what. It's under pressure, that is true, but air will not liquefy at room temperature even if you put it under pressure. Sorry, won't happen. So they have to use more complicated molecules. Historically, they included the chlorinated fluorocarbons, the CFCs, that are now no-nos because of the ozone layer. So now they use, these are hydrofluorocarbons. What is this? It will tell me somewhere. Oh, 1,1-difluoroethane. Yeah, it's a hydrofluorocarbon. So it's hydrogen, fluorine, and carbon in this stuff. It is a potent greenhouse gas. So releasing it into the atmosphere is still stupid. But for science, I'll release a little bit. Okay, so you probably have noticed that if you take it and just spray it out like as an air blaster, it comes out, looks like air. It's not air, but it's another gas. You tip it upside down, it comes out as a liquid because you're basically tapping into the liquid that's at the bottom of the tank. And I'm going to tap that liquid out. And it's bitter cold, and can I trap it in time? I think I trapped it in time, yeah. Okay, so I've got it in there. And I'm struggling to keep it in there because it's at pretty high pressure, but it's mostly a gas. There's a little bit of liquid at the bottom, and I could just fake you guys out. I could turn on the camera, we could watch it sort of, but the cameras are so iffy that I don't trust this. So there is a small amount of liquid at the bottom, and if I squeeze harder and make the gas more dense, I will shift the balance between liquid and gas towards the liquid. I'm forcing it to condense. And there's a little more liquid. Yeah, trust me, yeah, there's a little more liquid there, okay? And if I uncompress it, it evaporates because it's now the balance of liquid versus, actually it kind of works. You can see bubbles near the black, they're not there now. There are no bubbles near the black end of the tip. If I uncompress it, see the bubbles forming? And now I make the bubbles go away. And now the bubbles are forming. All right. And the rest of you all can just trust the gang up here, okay? And I'm getting tired of holding this. I'm going to let it go. Okay. Oh no. climate changed. Okay. I actually do feel badly doing this. I was like, oh, but a little bit, okay. So the idea is just make sure it's clear to everyone what's going on here. If you've got both the liquid and the gas present, remember you can have them in equilibrium, but temperature matters and pressure matters, or more importantly, density matters. If you make the gas high density, it lands more often on the liquid, and therefore the liquid becomes the favored phase, even at relatively high temperatures. If you uncompress the gas, so it becomes very dilute, the gas becomes the favored phase. Once a liquid molecule leaves to be on the gas, it's unlikely to return because the gas is so diffuse. So at high pressure, that favors the liquid. At low pressure, that favors the gas. Is that okay? And that's how air conditioners work. And this is not literally an air conditioner. It is a dehumidifier, but they're the same machine. This has 3 parts, and within them is a working fluid much like this working fluid here. It has what's called an evaporator, a condenser, and a compressor. And let's start at the evaporator, which for an air conditioner would be the indoor part. And the working fluid arrives at the evaporator through a thin pipe as a liquid. Liquid's relatively small, it's dense stuff, so you don't need very much of it. So you can send it through a little pipe, and it goes through a little pipe, through a valve-y structure that lets the pressure drop. Just like the pressure drops when you open a faucet, the water pressure is high before the faucet. You crack the faucet a little bit, the water comes out at low pressure. Having wasted all that, remember that pressure potential energy, it wastes it, it's thermal energy. This turns out not to be, the loss of thermal energy, of pressure potential energy is not an issue in this story. The main point is the liquid goes into the evaporator and is surrounded by low pressure gas, very low density gas. So the liquid evaporates. And as it evaporates, it needs its latent heat of evaporation. It soaks up the latent heat of evaporation from the surroundings. And this entire structure here gets very cold as the boiling liquid, the fiercely evaporating liquid, converts into a gas. This gets bitter cold. Actually, I can turn it on and it will be doing that. Hopefully not too loud. So this which was at room temperature, is, it's already 5 degrees below room temperatures. It'll get frosty shortly. So there's liquid coming in here, evaporating, and it leaves as a low density gas through this pipe. So it arrives as liquid through the little pipe, it leaves as gas through the big pipe, and it goes into the compressor. And the compressor's job is to take that dilute gas, like the piston in my syringe, and squish it. And as it does work as it squeezes the gas to high density, it does work on the gas. So not only does the gas go to high density, it also gets very hot, in part because work was done on it. So what came in as electricity through this wire becomes thermal energy in the gas leaving the compressor. So it's going to come out of the compressor. It's not too hot to hold yet. It's getting there. It's getting to the point where you don't want to hold your hand on there very long, because the compressor has done work on it. It's got hot. It's high density, high temperature gas, which then goes into the condensing section. The condensing section, in this case, has lots of little aluminum fins on it. It's doing everything it can to distribute that heat back out into the air. And this would be outside in an air conditioner. So this is the indoor unit getting freezy frosty, and this is the outdoor unit getting very hot. So heat is flowing into the freezy frosty indoor evaporator, and heat then is coming out of the very hot outdoor condenser. And more heat is coming out of the condenser than is going into the evaporator, because the electric energy that came roaring in through the wires is becoming thermal energy during the compression process. All right? So ultimately, more heat is dropped off outside than was soaked up inside, but that's okay because it's out, the heat's outside. But this does explain why, if you go by the outside unit of an air conditioner, including window air conditioning units, it's hot. It's actually, so you're in the summer, and the outdoor air is already hot, and you reach over the air conditioning unit's outdoor part, or the window unit, And it's actually hotter even than the outdoor air. It has to be, because it's got the heat that came out of the indoors plus what used to be electric energy. Is that okay with everybody? And this scheme works pretty nicely, and we're used to using it. So this shows up in air conditioners, it shows up in water coolers, it shows up in refrigerators, dehumidifiers, as is this one, and so on. Any questions about how this guy's working? Ideally, the working fluid stays in it for the rest of eternity. In practice, the things typically eventually leak, and so you have to have them maintained and so on. And now, I think they're getting better about when they're sort of decommissioned or worked on, they try to gather up the working fluid. They don't just like throw it out in the Earth's atmosphere, because again, it's not good in the atmosphere. It is a greenhouse gas, even if it's not an ozone depleting gas. Okay, I'm going to turn this guy off. This same structure can be used for heating a house. As I've described it so far, it's air conditioning a house. And so you put the evaporator indoors, the condenser outdoors, heat is soaked up from indoors and dumped outdoors, and that's that. But if you turn it around, okay, I'll be dramatic here, and I'll literally turn it around. Now, the indoor unit is the condenser, and the outdoor unit is the evaporator. And why would you do this? Well, in the winter, when you want to heat your house, you can operate this way. The house air is relatively cool. You want to make it hotter. The outdoor air is bitter cold. Why would you want to make it colder? This all seems kind of nuts. Well, when you operate it like this, what happens is the evaporator does become bitter cold, and heat flows into it from the outdoors. It's actually colder than the outdoor air, so heat flows into it. That heat is conveyed as chemical potential energy, actually, into the compressor. The compressor compresses it, an act which causes its temperature to rise substantially, and then the hot compressed gas goes into the condenser where it gets really hot and heat bleeds out into your house. So this device now soaks up heat from outdoors, even though it's 20 degrees outside, Fahrenheit, there's still thermal energy around. And so it gathers together some of that thermal energy, soaks it up, and dumps it into your house, even though your house is maybe at 65 degrees Fahrenheit and you're trying to get it up to 70. So we're using electricity to do this, so what is dropped off in your house is more thermal energy than was soaked up from outside. So I hope that's followable. And if I put numbers on it, and they're just approximate numbers, sort of pulled out of a hat, suppose that to heat your house properly over the course of a day, you need 10,000 joules of energy. An arbitrary number, okay? You want 10,000 joules of energy. There are two ways to heat your house to give it 10,000 extra joules of energy. You could buy 10,000 joules of electric energy and run a space heater in your house, just a toaster even, or just your hair dryer. Just turn that electric energy into thermal energy. Boof, you got 10,000 joules of electricity becomes 10,000 joules of thermal energy. Perfectly efficient, and I'll joke about that in a minute, okay? But you can do better. Run your air conditioner backwards. How so? Well, if you want to drop off 10,000 joules of thermal energy in your house, you don't have to make them entirely out of electrical energy. You can leverage the electrical energy. You can use 2,000 joules of electric energy to go gather an additional 8,000 joules of thermal energy from outside. It's there, it's abundant. Thermal energy is everywhere. Go gather some and carry it inside. That will cost you, say, 2,000 joules of electric energy. But you'll get it leveraged by the addition of 8,000 joules of thermal energy that was already around. So 10,000 joules will show up inside. Great, that's what you wanted. And it will only have cost you 2,000 units, 2,000 joules of energy from the electric company. Much less energy from the electric company. The outdoors got colder, but that's fine. You brought in its heat. Questions about that idea? So here in Virginia in particular, the temperature is mild enough that running a complicated machine like a an air conditioner / heat pump makes sense. The amount of electricity you need to pump heat from cold to hot depends on the temperature difference between the two. So if the temperature difference is relatively small, as it is here in Virginia, it's usually not bitter cold outside, and assuming you're not trying to make your indoor, you're not trying to reproduce the desert indoors at 100 degrees Fahrenheit, you're not moving heat from very cold to very hot. It's not a big temperature difference. So running one of these machines is quite efficient. You can use a relatively small amount of electric power to move a lot of heat from cold to hot if you don't move it across a big temperature difference. If you go way up north, at least before climate change, big temperature differences around, it becomes less appealing to use one of these complicated machines to move heat. They're not perfectly effective. They live within the laws of thermodynamics, but they never quite achieve what the laws of thermodynamics allow. They always have inefficiencies and imperfections. So go into the north and heat pumps become rarer. It gets too cold outside, and the cost of moving heat from bitter cold to indoors just becomes, you use too much electricity for every joule you move. It's not so obvious that it's worth doing that. Is that okay? So my jokey stuff about, how do I want to do this? Document camera. Document camera. There. Document camera. Every year about this time, you get advertisements like this start showing up in the local paper. You know, public rushes to get these amazing heating units, and this one, why they have Amish people selling these things, I'm not quite sure. I mean nobody any offense. They're talking about it being Amish, but it's like, these are just glorified space heaters. These are devices that take electricity in. You purchase 1,000 joules of electricity from the power company, you make 1,000 joules of heat. They are 100% efficient, which they're often very happy to say. And here's another one. How it works. 49% savings. Why not 51? They just make up the numbers. These are just glorified electric heaters, nothing else. And they are exactly 100% efficient, which many of them will tell you. I had to hunt around for them. They turn 100%, because energy is conserved. What can they, if they were 99% efficient, that would be miraculous. But nope, they hit 100% exactly because of conservation of energy. But you can do better. The point, okay, laughing aside, is you can always do better. Don't just turn ordered energy into disordered energy. Use the ordered energy and move already pre-existing thermal energy around. It's much more, you still have to live under the laws of thermodynamics, which constrain you, but in terms of energy efficiency and ultimately, therefore, in the future of this planet, it's a good thing. Move the heat around, don't make more. We got plenty. Okay? Back to, all right. So that's my story, I think, of heat pumps. Oh, one other thing to show you, just because it's kind of cool, is not, there are heat pumps that don't involve these working fluids, and you may well have seen them. There are a number of ways to move heat around. They all have to live under the laws of thermodynamics, particularly the law of entropy, but one of them involves, the classic one involves the movement of heat. How to describe this? It's the Seebeck effect. I can't remember how to describe it in detail, but it's thermoelectric devices. There can be a relationship between it's hard to, I'm stuck on how to describe it. Thermoelectric device uses electric power, again, to move heat from cold to hot, but it does it with solid state components. And motivating why that works, which is what I'm trying to do in my head, takes some doing. But it does work. the object I've got up here, and I'll zoom in on it in a second, we've got two thermometers reading the two sides of this thermoelectric device. And when I run electric current through the thermoelectric device, it will move heat from one surface to the other. And so I'm now running electric current through it. Let's zoom in on it. Camera, preset one, yeah. And you can see it over there. One side's getting hot, 38 Celsius. I'm in the screen. And the other one's getting cold, 16 Celsius. So we're refrigerating one surface and heating the other surface. And the heated surface gets significantly hotter than the refrigerated surface gets cold, because this movement, this pumping of heat from the cold surface to the hot surface naturally consumes ordered energy, and that ordered energy is dropped off in the hot surface, which is getting really hot. 60 degrees Celsius is not boiling water, but it's getting there. The other one's at 13 Celsius. I have ones in my lab that get down below freezing, and they start getting ice all over them. So thermoelectrics, they appear in, like, you can get a cooler that in your car you can plug in your chilled thermos to make cold beverages while you drive. Of course, you're not supposed to drink them while you drive, but okay, that's another problem. Yeah. All right. Setting aside air conditioners, the question came in about my unrelated to physics, or at least, do my ear jelly products sell well? So from a few of you may know that for the past zillion years now, actually more like 10, I've been developing a material that is kind of a solid version of silly putty. By solid version, I mean silly putty, you play with silly putty, I hope, and it has weird properties. When you bang out with a hammer, it's hard. When you pull slowly, it slurps out, it's soft. But it has no fixed shape. So once you pull it out, it doesn't remember that it was a different shape earlier. My materials remember, so that you can have an object that will have a fixed shape, but you can pull it out of shape, and it will keep that new shape for a while, and then go back to its old shape. And so this is the first product we're trying to make out of this that we have made, and it has gone well so far, but we're still a work in progress, is earplugs. So you can take them out of shape, pop them in your ear, and then they slowly go back, or try to go back to their real shape, their official shape. And when they encounter your ear canal, they stop, because they only have a very weak opinion about what their permanent shape should be. And so they encounter trouble, it just stops. And so they press very gently against your ear, so that you barely feel them, but they seal perfectly, and they keep sealing perfectly. So they're actually pretty good, if I say so myself, and it's a long process. I would say the connection between academic science and the real world of making things, there's a vast separation between them, unbelievable separation. And crossing, parts of this are described as a death valley, and trying to go across that is nearly impossible. But we'll get there eventually. So that's unrelated to what we're doing right now, but something that keeps me up at night. Anyway, I'll do it. Automobiles, I'll start automobiles on Monday for both of you who are here. Yeah. Have a good weekend and/or week.